All right, today we're going to look at section 6.4, oops-a-daisy, which is about proof and problem solving with these new trig identities that we've developed over the past few lessons. So my advice on these new trig identity pieces is that you'd want to start on the side with the place where you can use one of these new identities. So I'm going to start with this double angle for cotangent. Now we don't have a double angle formula for cotangent. So the first thing I'm going to do is I'm going to think about that as the reciprocal of tangent. So I'm going to write it like this. Remember that -1 when it's outside a parenthesis, right? That just means a reciprocal. It's not talking about the tan inverse, just talking about a reciprocal. Okay. And now what I'm going to do is I'm going to use my double angle formula for tangent. So I'm going to replace tangent of 2 alpha with 2 tan alpha over 1 minus tan squared alpha. And still have that to the -1. So I'm going to go ahead and do the reciprocal now. So I'm going to get rid of that -1 exponent by flipping the fraction. And now those guys, the 2's, are going to cancel out. And what I'm going to do next is I'm going to separate this fraction. Notice that my denominator is just a single term. So I can separate this fraction as like 2 things with a common denominator. That common denominator being tangent alpha. So I have like 1 over tan alpha, and then minus tan squared over tan alpha. So those have the common denominator, so I could subtract them back together and get back to the previous step. I notice that tan alpha and tan squared alpha have a factor in common, so those can reduce. 1 over tangent is cotangent alpha. And then we have just the tan alpha left over here, and that is exactly what we're looking to get to. So we're done. Okay. So next up, again, I would start on the side where the identity is easily observable. So now I could use cosine of 4x. So what I'm going to do is I'm going to think about this as cosine of 2 times 2x. Because I want to use one of my double angle identities. Now, remember the double angle identities for cosine, there's like 3 of them that we can choose from, right? The one that I'm going to choose is the 1 minus sine squared, or 1 minus 2 sine squared x. That's the version I'm going to choose. I want either the 1 minus 2 sine squared x or the 1 minus 2 cosine squared x, because I have the 1 minus here that I'm shooting for. And I don't think it will really matter a whole lot which one we end up picking, but that's the one that I chose when I did this. So again, this is like my my x. So like this is cosine like 2 theta, and 1 minus sine squared, 1 minus 2 sine squared theta. but my theta is really just the 2x there. So I have this. And now I can think about this as like 1 minus sine 2x times sine 2x. And I can do my double angles for sine. And this is now in hindsight, I'm really happy that I chose the 1 minus 2 sine squared as my double angle option for cosine 2x, because the double angle formula for sine is way easier to use than the double angle formula for cosine was going to be. So I have this. This is all just stuff multiplied together, so I can multiply it in any order I want. So 2 times 2 times 2 is 8. Sine x times sine x is sine squared x. And cosine x times cosine x is cosine squared x. And that's exactly what we're looking for. So we're done. This trick here, where we took 4x and wrote it as 2 times 2x, so I could use a double angle identity on there, is a rather common trick. It's a good one to remember. Okay, we've done a bunch of other proof kind of along the way, so that's going to be the end of my proof examples. I do want to do some solving examples now. So here we're asked to solve algebraically on the interval from 0 to 2 pi of cosine 2x equals sine x. So the issue here, the first thing we need to do is we need to rewrite this so that the variable has the same coefficient in all of my trig functions. So the obvious thing to do would be to rewrite cosine 2x as something with just a regular x in it. So I would use a double angle. So again, cosine has 3 options. Since the other side is only a sine in it, I want to pick the option for cosine 2x that has only sine x's in it, namely 1 minus 2 sine squared x. And I want to do that because on my next step, the factoring can only happen if I have all the same trig function. So I'm going to move everything on one side. So I have 2 sine squared x plus sine x minus 1. So I added the 2 sine squared x over, subtracted the 1 over. What I'm left now is something that's factorable, but the leading coefficient I notice is not 1. So I have to do that long factoring. So I need to find like the 2 things that multiply to give me a times c, the leading coefficient times the constant term, but still add to give me b, the linear term coefficient. So the things that multiply to give me -2 and add to give me 1 are 2 and -1. So what that allows me to do is to rewrite the linear term sine x as 2x plus -1, 2 sine x plus -1 sine x. That's all equal to 0. I'll make 2 groups where the plus sign is in the middle of the group. I'll factor a greatest common factor from the first group, which should be 2 sine x, and factor a greatest common factor from the second group. That would be a -1. I notice now if I look at this piece and this piece, there's a sine x plus 1 in common to both. So if I factor that out, I'm left with 2 sine x minus 1. So there's my factored form. Oops, running out of space here. Yuck. Now come now. Oh my goodness. be difficult then. I'll then apply the zero product property. So this says sine x is equal to -1. I know that if I go to my unit circle, the only place where the y-coordinate, because we're talking about sine, so I'm looking at the y-coordinate, is -1 is at 3 pi over 2. So there's a solution. And here I will add 1 and then divide by 1/2, or divide by 2, giving me sine x is equal to 1/2. So when I go to my unit circle, the only place where the y-coordinate is 1/2. Well, there's actually two places, right? Because sine is positive in the first and second quadrants. That's at pi over 6 and 5 pi over 6. So those are my 3 solutions. Okay, let's do another one. Here we have sine 2x is equal to 2 cosine squared x. So my first order of business is going to be using my double angle identity on sine 2x to rewrite that, because I want to get all of the coefficients on my variables to be the same. I'm then going to not divide by cosine x, because I don't want to lose my solutions. Instead, what I'm going to do is I'm going to add the 2 cosine squared x to both sides so that everything is equal to 0. I'm going to factor off the greatest common factor. That's a cosine x. Oops, let's make it a 2 cosine x that I should be factoring off. Doesn't really matter there if I took the 2 or not. Oops. Okay. I can apply the zero product property. To set each of the factors equal to 0. I divide both sides by 2, and I just get cosine x is equal to 0. And that happens on when x is equal to 0, so that happens at pi over 2 and at 3 pi over 2. Neither one of those are inside my desired interval, so I can subtract 2 pi. That would give me -1.5, still not in between, so I subtract again, so that would give me -3.5. We'll do this. Okay, so that's in between. This is 1.5 pi. That's not in between the interval I'm looking for. So I'll subtract 2 pi from it. -0.5, still not there. Subtract 2 pi again, I'd get -2.5. That is inside the interval. So I have these 2 solutions. This guy now, I'm going to subtract sine from both sides. And then divide both sides by cosine. And I want to do that because sine over cosine is tangent, and I'll move the negative sign over. And I know tangent is equal to -1 in the second quadrant and the fourth quadrant. Again, neither of these are on the interval that I'm looking for, so I'm going to keep subtracting 2 pi till they are. So this is 3/4. Subtract 2 pi from that, I got -1.25. That's not enough. Subtract again, I'll get -3.25. That is in between there. So what is that? That's like 15 pi over 4. And then same thing here. I subtract 2 pi once, I get -1/4. Subtract it again, I get -2.25. That is inside there. So that's going to be -9 pi over 4. Ooh, this was supposed to be 13. I can't do my arithmetic. Sorry, negative 13 pi over 4. And then I got one more example to do. So here I have sine squared theta is equal to 2 sine squared theta over 2. So what I'm going to do is, again, I want to work on this piece first because I want to get rid of that theta over 2 piece. So I'm going to use my half angle identity. So that's plus or minus the square root 1 minus cosine theta over 2. But that's for sine of theta over 2. I have sine squared, but whoa, that's even better, Mr. Kulik. You know what that sine squared is going to do? Well, it's going to cancel the plus or minus, and it's going to cancel the square root. And boy, howdy, that makes life quite a bit simpler. And even better, look at this. The 2's can cancel. Woo! I like what's happening here. So we have sine squared theta equals 1 minus cosine theta. All right. Got a little bit of a problem, though, because this is kind of irreconcilable because I have this extra 1, so I can't just like divide by sine or cosine and try to make a tangent out of this. It's just like kind of a mess. So what I'm going to do is I'm going to rewrite sine squared in terms of cosines because the other side has just cosines in it. Well, I know 1 minus sine squared is cosine squared. And that is quite excellent. So now if I subtract 1 from both sides, get out of there, 1s. And then if I add cosine squared to both sides, I get 0 equals cosine squared theta minus cosine theta. And hey, that's not so bad. I can factor that. I'll just pull off a greatest common factor of cosine. Oops. That's a 0, not a theta over there, Mr. K. Oh, I know. I'm just making mistakes. So we have that. Now, since it's factored and equal to 0, I can apply the 0 product property. Cosine is equal to 0 at pi over 2 and 3 pi over 2. But it's asking find all solutions. So I could take each of those and plus 2 pi k to them. Or I notice that pi over 2 is 1 pi away from 3 pi over 2. So I could combine those two solutions, and instead of writing them separately plus 2 pi k, I could write just one of them plus 1 pi k. And I will do the other piece. So we'll add 1 to both sides, and I'll go to my unit circle. Cosine is equal to pi at 0. That's the only place it's equal to 1. I'm sorry, cosine theta is equal to 1. Did I say pi? I don't know. Add a stroke or something there. Anyways, but it's all solutions, so all I do is slap a plus 2 pi k on the end of that. And we are good to go. So that is my solutions. And I'm all donezo's there. At this point, you should be able to do the entire problem set. So you should be able to do up through 42. Sunday will be the last homework check for the semester. That homework check is 1 through 42. Reminder that one homework assignment is dropped per semester. So if you've completed all the homework assignments to this point, and they're all full credit, Nothing is really being dropped, so you could choose to not complete this homework assignment, and it would not affect your grade. Now, I say that because I know you're all excellent students, and you would eventually complete this homework assignment. But it's a busy week, and you may have bigger fish to fry in terms of finishing papers and projects and portfolios and whatever before exams. And you might just say, I'm going to kick the can on this Chapter 6 stuff for a couple of days while I wrap up my English papers or whatever I have to do, and not worry about the due date for this homework assignment because it's going to be your drop anyways. So you can always think about it that way. Anyways, that's it for 6-4. Again, continuation of just the ideas we had in Chapter 5. We've just added more identities that we can use to do them. So that's it for me. Have a great day. Bye-bye.